We did a lot of calculations in the last videos, and we calculated how much mass you would need, spring mass you would need to store a certain amount of energy in. Well, this energy storage, this specific energy formula that we used, is assuming that all the material is taking part in this energy storing. Which is not always the case, because if you stretch a material, then yes, all the material, all the particles in this bar, for example, that you stretch, is taking part in energy storing, because it's all the energy all the mass particles, the spring particles, are stretched to its limits. But if you do not stretch a material, but you bend it, for example, here in this little figure that I drew here, then if I place a bending moment to a bar that's stretched out from a wall with length L, and here I amplified a little bit of it, then you see that the stresses, the bending stresses, are only maximum at the outer surfaces of this bending bar. In the middle, the stress is 0. That means all the mass of the spring that is located in the middle of this bar is dead weight to your spring. And then the stresses get higher and higher up until the surfaces where the stresses are maximum. So you can imagine that the energy storage capacity of this bending bar is a certain factor away from the maximum energy you can store in the same material when stretched. And in this video I want to calculate how much this factor is. So how much more mass would you need to store the same energy in a bending bar when compared to a bar that is stretched? Okay, well, let's first consider the E maximum that we could store in this material. A bar with length L, with a width B and a height H. And how much energy could we store into this bar? Well, that is the specific energy, of course, the maximum. If we would stretch it to its max and then all to its max, so when we apply a tensile force, then we would get 2 times Young's modulus times the density times the mass of the bar, which is B times H times L times density. So we can delete the densities, and then we get for sigma, sigma is m times a half h divided by the moment of inertia, and if we insert it into this formula there, then it will be all squared, and we get m squared times b L, and the h is also there, should be squared, so h to the power of 3. Then we get a half, in this will be squared, so it's a quarter, and here's a 2, so this will be a factor of 8. Young's modulus and the moment of inertia squared, because the sigma was squared. So here we have the formula where we can calculate how much energy you could store, the maximum energy you could store in this material with from this bar with width B, height H, and length L. Okay. But now, how much energy do we store when we bend it? Now, let me show you this. If we have the bar and we know that the stresses grow bigger when y is bigger, y is 0 at the neutral plane, The neutral plane lies exactly in the middle where the stresses are 0. So y is going upwards from 0 to half h. And we know that the stress is m times y divided by the moment of inertia. Then we can calculate for this little plane here, the blue plane, how much energy is stored into one plane. The advantage of looking at it this way is that the stress is now a constant for this blue plane, so we can use the energy formula, and I call it d energy because it's a little part. This is a very thin layer, a thin plane, and we can later sum all the planes up and get all the energy in the bar. Well, let's see. We use the same formula that we derived earlier of the specific energy, and then we multiply it by the mass of this little plane. And the mass of this plane is b times L times this I call dy times the density, and the density again disappears. So if we calculate this and we fill in this formula for the stress and we square it, then we get the total energy we can store into this in this bar. And we would have to sum up all these little layers, and I will cut it into half because the stresses are the same on the lower part as on the upper part, so I will just consider this upper part and then multiply it by 2. So I will say I will let it go the integral from 0 to a half h. So this is half h, and then I take sigma squared. Oh well, let's do it directly. M squared times BL, let me take the y outside, the y is squared, and then the E, we have 2 times the E times the moment of inertia squared. Here we have the formula for the total energy you can store into a bending bar. We have to calculate this one, and this is an easy one because it's only y to the power of 2, so it will be 1/3 y to the power of 3, and we fill in this half, so that will be 1/8. These can cancel out, so we have 1/8 times the 1/3 of this integral, 1/3 of this integral, m squared BL h to the power of 3. There we have it. So let's say MBLH 24 EI squared. This formula, which tells us how much energy we can store in a bending bar, is now a little different from the one we derived earlier, which was 1/8. So the difference between bending and stretching is a factor of 3. You can store only 1/3 of the energy into a bending bar when stretched the outer surface to the limit than when stretched to the limit, because then all the material is joining into the energy storing. So we have a factor of 3 in bending.